So as I say, we ran a first sample of the Molly problem between the 11th and 20th of October. We actually worked in collaboration with the Technical University of Munich to run the survey. There's a little background, which I've just mentioned before, which was all about engaging the public in a very different debate around self-driving ethics and what they expect in terms of behaviour of self-driving vehicles. The survey had 296 respondents during the 2-week period, 70% male, 25% female. Ages were between 18 and 73, a mean of around 41. People lived in rural, city, suburban areas, but mainly respondents were from urban environments. 94% of them held driver's licenses, and 3/4 of the respondents were both willing and excited to travel in an automated vehicle. So these are not technophobes that have responded. These are people that are actually positive towards the technology, but they have certain expectations. So some of you may have seen the formulation of the Molly problem before. It's just simple. A young girl called Molly is crossing the road alone and is an unoccupied self-driving vehicle. There are no other eyewitnesses. So this is the scenario, and the real question we were posing is what should happen next. Now, the scenario itself, you'll notice, is incredibly stripped down compared to what you might expect in, say, a scenario testing verification and validation process. So it doesn't actually specify anything to do with the roads, whether they're in the urban environment, a rural environment. It doesn't specify the class of vehicle, doesn't specify whether it's at day or whether it's at night. It doesn't specify whether Molly is crossing a legal footway or pedestrian crossing, or she's stepping out between two parked cars. It gives none of that information to the respondents. So what they envisage could be any of those scenarios. And what we were trying to do is make sure that this is applicable no matter what country you're in, no matter what the driving situation is. So yeah, next question, what should happen next? I'll go through all of the results now, and then we can have a discussion at the end. So I won't go into too much detail, but 97% of respondents say the software should be aware of the collision. That sounds pretty simple. It sounds pretty logical. Actually, it's one of the hardest things, particularly when you're dealing with a child pedestrian impact. But the public expectation is that 90%, 97% believe the software should be aware of the collision. Based on that awareness, the public then also expect that the software, in the event of the collision, would stop at the collision site. But again, it can't stop unless it's aware. So first is the awareness, and then it's a question of what do you do once you have that awareness. Stopping at the collision site, 94% of people said yes. 97% of people then expected the software to be able to indicate a hazard. Now, we didn't specify exactly how to indicate the hazard, but the expectation is obviously being able to put on the hazard warning lights, for example, or if there was a V2V solution or V2X solution, be able to communicate to other road users that there was a hazard in this location. So again, 97% said yes. 94% of people then believe the software should be able, if necessary, let's say, to call or to alert the emergency services. And all of this is predicated on detecting the collision in the first place, and then a set of behaviours that come after it. I think what's really important to recognise is that those 4 questions all relate to the Convention on Road Traffic. So the 1968 Convention on Road Traffic does specify behaviour in the case of accident. It does specify all of those behaviours. Now, we didn't tell the respondents that at the beginning of the survey, but we're now talking about a document that's, if I do my maths correctly, I think more than 50 years old, I think. Yet the expectations remain, regardless of whether they're for a human driver or for an automated driving system. And so you can see why those let's say, requirements of driver behaviour were put into the Convention on Road Traffic and were agreed across all of the countries that are now signatories to that convention, because they are universal. These don't necessarily apply to automated driving systems, and it's something that we can discuss at the end. So having captured that information, what we're then looking for is really to do with what data should be recorded, what should be able to be recorded and then recalled. So elements really that link towards explainable AI for the software itself. Again, there were overwhelming majority have very strong and clear expectations for explainable AI, which I think is incredibly valuable for us to know as an industry. And now I'll go through the points that we specifically raised. So 99% of people would expect the time of the collision to be able to be recalled. So you should be able to recall the time at which the collision occurred, which I think is a very fair expectation. Again, 99% said yes, the location. So the time and location where the collision occurred. So were you at the scene at the time of the accident is the other way to look at it. 99% of people expect that. We then went on to say, should it be able to recall when the collision risk was identified? And so the collision risk, 93% of people expect, yes, that should be something that could be recalled by the software. The collision risk could be that Molly is detected in the road directly ahead of the vehicle, or it could be that there are levels of occlusion in the environment that could lead to a collision. Let's say if you have a possibility that a collision could occur, someone could step out at the very last minute. So we didn't, again, specify how to identify collision risk, but respondents felt that that should be something that the software would be able to explain after the fact. 96% of people then expected the software to be able to record if Molly was detected. So again, being able to say that, yes, there was an object in the environment and that object represented Molly. So 96% of people expected that behavior. Again, 96% also expected not only that the object was detected, but when that object was detected. And that becomes very important when you start to look at, okay, well, how much time did the software have in order to respond to Molly being in the road? Was she there for 5 seconds? Was she there for a second? All of that goes towards understanding whether the accident was reasonably foreseeable and preventable. Additionally, we asked the respondents about whether it was important that Molly was detected as a human or not. So 91% said yes. What's interesting is that within the Elaine Herzberg fatality, at no point was she detected as a human. At no point was she detected as a pedestrian. She was detected, a bicycle was detected, which you could indicate was, well, if there's a bicycle in the road, then it has a human on it. But at no point was it explicit that there was a human that was in the road. But 91% of people expect that it should be explicit. And then 90% also said when Molly was detected as human. So again, if you look back at the Elaine Herzberg fatality, you could say, right at the very beginning, yes, there was an object that was detected that represented Elaine Herzberg, but its classification changed throughout the time of that detection. And so when it was detected as a human also becomes important, not just when was it first detected as an object. Then we move on to sort of the mitigating actions that people expect. And so 98% of people whether a mitigating action was taken to be recorded. So we're talking about, yes, there's been a situation that's been detected, there's been a high risk, and therefore there is a choice of action that's taken. So what, effectively, was there actually some mitigating action that was taken as a result of the risk that was perceived? Then 97% of people said when that mitigating action was taken, Obviously, that's then can be related to, okay, well, when was Molly detected? When was the action then taken? So you get the chain of causal events occurring, and then what that mitigation actually was. So 96% of people were interested in what that mitigating action was. So all of that enables you to, the information gives you some indication to do accident reconstruction, but it gives you some awareness of what the software was thinking at that time, which is really where the explainable AI part becomes really important. Now, if this was a black box, let's say pixels pedals approach, you can see that for more than 90% of the public, that would not be acceptable. It wouldn't be acceptable to not know the information that they've requested in this survey, in responding to this survey. So I think that's really important for us, again, as engineers that are designing these systems. So after that, we went on to look at 2 additional questions, and then we can open up for questions ourselves in this session. But the 2 additional questions were about, should similar recall capabilities be available for near-miss events? And what should happen if those recall capabilities aren't available? So 88%, nearly 90, 88% would expect similar data recall abilities for near-miss events. So not only are we talking then about collision events with pedestrians, for example, but in this case, a near-miss event with a pedestrian. And this was framed as Molly jumping out of the road to avoid the collision. So Molly, in this case, was the one who had to take avoiding action. Car that can, self-driving vehicle that continued to drive towards her. And if she hadn't have taken the avoiding action, there would have been a collision. That's perfectly understandable that the pedestrians and other road users would expect that type of near-miss behavior to be captured and recorded. Yet we struggle enough to record pedestrian impacts, let alone define a near-miss event. So that's has a massive impact on the data recording capabilities for self-driving vehicles. And then the final one was, what would you expect to happen if the software didn't have that capability? And 73% of people said that they would expect it to be prohibited from driving. So basically, if the car was on the road, recording data fine, but then there was a problem with the recording, effectively they would expect it to stop. Or if the vehicle doesn't have that recording capability in the first place, they wouldn't expect it to be on the road. And I think that shows how strong the public's opinion is regarding the data and insights and the explainability that's required for these self-driving systems. Now, the next piece of work that we're going to do with Technical University of Munich, we'll look at extending the Molly problem and combining it with the traditional trolley problem type ethical dilemmas. But really what we're using this survey for is now to feed into the work of the IT focus group that I chair, and they will become criteria, we'll hopefully approve next week in our focus group meeting. They'll become the criteria for defining data standardization. The data that we're expecting to standardize will be what's required for an AV to publish in order to make a continual assessment of driving behavior. So hopefully that's given you a little bit of an overview of the Molly problem. I can then touch on during the questions, how it impacts with other standards or regulations that were kind of described in the presentation. But I thought, given it was a meetup, I thought we could have more of an open discussion. If you need any of my contact details, they're all on the screen at the moment. So thank you very much.
Thanks, Brun, for this kind of really interesting numbers and survey, the results you presented today. So first, are there any questions from the attendees? Please note that you can pass that question in the Q&A chat. While you guys are thinking, I have one. So, I mean, you pointed out clearly the expectations. From your point of view, what should be implemented software and hardware-wise to fulfill that kind of explainability. What are your thoughts or your expectations?
Yeah, well, what we're working on within the focus group, the IT focus group that I'm chairing, is really being able to standardize the data that's published from an automated driving system. Now, that data isn't something that's required. In actual fact, when you look at, let's say, UNEC regulation for event data recorders, they're based upon triggering events, which the Molly problem, actually colliding with a pedestrian, wouldn't trigger recording by an EDR. So actually, there's no requirement to store any of this data for any of the developers anywhere in the world at the moment. And I think that's the thing that we need to be really clear on. If we're going to build trust with the public, there are two sides to building trust. One is don't hit anybody in the first place. You know, that's a good way to build trust. But the other one is if you do hit someone, be able to explain what happened and be able to learn lessons from that and make sure you can prevent those collisions from happening again. If you're recording the data, then effectively you can't prevent those collisions. And what I think is even more important is it's just about collisions. I know we focus on that a lot because we always work with kind of lagging metrics, but near-miss events are leading metrics. Near-miss events are the things that can indicate poor behavior before the collision occurs. And that recently in the sort of RAND report, you know, the Safe Enough report that was published a few weeks ago, those leading metrics or measurements are considered the gold standard, really, for safety. So that's where we need to be heading, you know, this sort of continual monitoring that's able to detect near-miss collisions.
Okay, thanks. Yep, makes sense. Just saw that there are some questions on the chat. So we have one question is that new cars call the emergency service already today if you're in an accident. The question here is the overall goal that the car call emergency vehicles also for smaller accidents with less damage on the vehicle? Right now, if a vehicle hit Molly, no emergency services would be called.
Yeah, that's exactly right. Yeah, that is exactly right, because it's based again on those triggering events. You know, so the same triggering events that would trigger an EDR recording would trigger then the call of the emergency services. But there's normally focused around the occupant inside the vehicle. So you know, the thing behind eCall is really to you know, again, improve the situation for the occupant, for the driver, for the passengers. But when the majority of accidents and fatalities occur with pedestrians, we should be thinking about how we extend those systems for pedestrians, even for human-driven vehicles. Yeah, but I think it's especially important for automated vehicles. And the reason I mention that is because if you cannot detect a collision, you are at risk of having a hit-and-run accident, a hit-and-run collision with a pedestrian. And that, in terms of the industry, will be devastating. I've just been going through this evening, going through the NTSB report again for the Elaine Herzberg fatality with Uber in Tempe. The vehicle was not aware that it had had a collision with Elaine Herzberg. There were systems in there that in retrospect you could look at and say maybe that would have provided some indication, but there was actually nothing concrete that would indicate that you'd had a collision with a pedestrian. And therefore, none of those conditions, those first four questions, would have been acted upon. It's only because there was a human safety driver in that vehicle that the vehicle stopped and that all the other things occurred, basically, like calling the emergency services and everything else.
Okay. There's a second question. Is a built-in video dashcam style function expected or suggested that records the last n seconds and store all that stuff in case of a collision for, let's say, human assessment afterwards?
I think the issue with human assessment, and it's very natural for people to go to dash cams immediately to have this sort of independent source of data. Again, you could see from the Elaine Herzberg fatality, that was the first piece of information published. It doesn't indicate what the vehicle actually saw. So that the work that we're doing within the focus group looks much more at requesting perception state data, local world model data from the automated driving system. So that's effectively allowing the ADS developer to choose whatever sensors they want, use whatever sensor fusion techniques they want. But the expectation is that at the end of that process, there is a local world model, a description of the 3D world that surrounds the vehicle itself. And that is one of the key things that we should be tracking on a continual basis, you know, the stability in that local world model. And then attached to that should then be the uncertainties of the model itself, and then the level of risk that's experienced in the environment. And then the final thing to track, which is really important, is then the output vehicle dynamics and any of the other safety systems that were triggered. So they're really the three things. What did you perceive in the world? What risk was perceived? And then what action did you take? That formed the basis of a continual monitoring system. So it's very much like a telematics-based insurance system, you know, that we use for human drivers, where, you know, you monitor the vehicle accelerations, build up a profile, but you're able to put those accelerations in the context of the environment. And I think that's what's really important. That's the big step that we can make with the autonomous driving systems or ADAS systems.
Okay, so maybe a last question, then we have to move on. So there's a question: if you could inspect all road accidents like this, wouldn't this in the long run mostly lead to the statement the human behaved stupidly on the road?
Yeah, I think there's a very good case to make for, yeah. You know, we say at the moment 96%, I think it is, of accidents are, you know, down to human error. I'd like to remind people that almost 100% of all active agents within the environment are human. We haven't seen any of those statistics for automated driving systems yet. But yeah, I think one of the really interesting things is, and I'm aware of this being used on within the airline industry, is that if you have a collision avoidance system, it's likely that your vehicle won't be involved in collisions. That's the aim. You know? So to validate that for the airline system, because the system would avoid the collisions, what it was able to do was flag up potential collisions that could occur from other agents in the environment. So two planes that might be flown by humans that might come close together. And it was able to use that to say, look, I can spot what a collision could look like. So you could take exactly the same philosophy and apply it to the road. So the self-driving vehicle is not only monitoring its own behavior, it's also looking and assessing the behavior of all the other drivers in the environment. So that is an interesting side effect.
Yeah, absolutely. So just looking on our timekeeper, Jing, do we still have room for one question, or?
I believe so, since we started later. So maybe let's just allow another question. But I think Brian will stick around, and you can just continue our discussion in our chat or Q&A. Yeah. So let's allow another question.
Okay. Then I saw Felix has a question. A last comment, Bryn, from the chat is that it would be helpful to validate the vehicle perception versus the human perception, just to consider explainable AI. It's not a question, it was just a statement on your question, or on your answer.
I think I've said a few times recently on social media that the thing that we're missing at the moment within the industry is being able to evaluate the OEDR capabilities of the ADS. So the object detection and response. Yeah, that's not something that we measure. The SAE definitions don't tell you how good the OEDR capabilities are. Whether the system is level 0 or level 5, you have no idea. And the challenge that you have with, let's say, with a level 2 system, for example, is that you don't know what level the consumer, the user, assumes the OEDR to be functioning in. And at the moment, many assume that it's a lot higher than it actually is. And that's why you end up with these non-attentive accidents. So I think focusing on OEDR capability is really important. And I think that's really what we're focusing on with the focus group. You know, how do we start to make that assessment? And then yes, comparing that to humans becomes really important.
Yeah, that's indeed really interesting approach. So then come really to our last question. Felix, it's your turn.
Thanks. Yes, Bryn, I was wondering about this because you've asked a lot of people these questions, and depending on whom you ask, you'll get different answers, depending on whether you ask people from within the AV industry or at least, I don't know, software developers, perception engineers, computer vision engineers, or the general public, right? And I'm pretty sure that you've thought of that, and that this is represented, and you probably have like your study has collected this kind of metadata as well. But what I'm wondering is, like, if I was the general public, I would tend to say, yeah, sure, on all of your answers, on all of your questions. I would say, should it be detected? Should it be recorded? Yes, of course. Always yes. So isn't there a strong inclination of a person who is not directly familiar with the subject to just say, yeah, sure, go ahead. I want you to do everything you can in order for the self-driving system to be safe, and in the end, that will make it unfeasible.
Unfeasible in terms of the amount of data that's required to be recorded, you mean, Felix?
Yeah, in terms of the requirements you impose on the system. I mean, the question set you have provided now can also only be the start. You can go further and ask people in the general public how often they think they like accidents will occur and so on and so forth. And very likely you get numbers that are just impossible to reach. So what's your take on that?
Yeah, I think it's all about within the focus group. Our activities are really trying to define the minimum set of data that's required to answer the public's questions, you know, the responses that we've had, and not be too onerous on the developers. You know, the worst case for developers is record everything all the time. And by everything, I mean all of the raw sensor data. But there's nothing in what we've defined in the Molly problem that requires you to record raw sensor data. All of that information can be recorded based upon the local world model and the accelerations of the vehicle, and some insights into the level of risk that the software was perceiving within the environment. So those parameters actually become much more feasible for us to record and meet the requirements of the public's expectations for explainability. You know, when asking the public aren't specifying, yes, record all raw data all of the time, you know, because they want explanations. They don't want raw data. So we're looking at is there should be a level of explainability that's continual, rather than actually, you know, record the raw data, process it afterwards a collision's occurred, because that's irrelevant for near-miss events. You'll never be able to do that for near-miss events. So the key thing is creating those triggers for near misses, and then limiting the amount of data that we store and record so that it's meaningful enough, but not onerous on the developers. That's the key thing.
Okay, so I see a lot of questions here, but yeah, we have to move on now. So, Bryn, I think you're around here, so you guys can.
Yeah, I'll take a look and answer in the chat.
Yeah, you can chat with Bryn, or maybe you can follow up on LinkedIn. So yeah, then I pass over to Jing, and then please announce our second talk.
Yeah. So thank you very much, Brian, again, and thank you, Florian, for handling the questions. Then let's welcome our second speakers, Felix, who is the co-founder and managing director of Insenda AI, and also the co-organizer of this series of autonomous driving, of course. And his topic is on data quality and reliable machine learning development. Felix, the floor is yours.
Good, we can see your screen.
Okay, there's a new unmute button. Awesome. Good.
Yes.
Glad you found that there.
Good. Thank you very much for introducing me, Jing, and I come right to the point. So I want to talk a little bit about data quality and reliable machine learning. Recently, within Senna, we have been collaborating with Suite, and like we compiled an extensive white paper on the matter, and I'd like to share some parts of that today. And yeah, let's get started. So first of all, there's some cartoons and lightweight content for the introduction. So maybe you've seen that one already. It's like one person sitting on a pile of data, and the other one says, "This is your machine learning system." The guy in the pile of the data says, "Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side." The first guy says, "What if the answers are wrong?" And he says, "Just stare at the pile until they start looking right." And then there's another thing I wanted to point out. Many of you may know that already too. It's a post that, or Andrej Karpathy used this slide, this chart here in the slide decks. He's the director of artificial intelligence at Tesla, but before that he was with Berkeley University and held some very popular machine learning, deep learning courses. And he essentially said, if you're a PhD, then mostly you focus on the models and algorithms, the neural networks, how you define them, and at the fraction of your time you think about the data, you sleep about over that, right? And him being at Tesla, like it starts to become his main problem, the main reason why he loses sleep, and the models and neural networks they actually go a little bit into the background. And there's also a very nice paper by Google, which is called Hidden Technical Debt in Machine Learning Systems. That also elaborates on the fact that like your machine learning code is actually just a tiny little bit of the overall environment that you will have to implement and maintain. And there's a lot of and it's pretty easy nowadays to download TensorFlow, download some Jupyter notebooks and get something to run and something to classify a couple of images. And that seems like it's so easy and so straightforward that you can just do that and save a lot of time over conventional engineering. But the truth is that implicitly, like in the background, it comes along with a flood of additional work and additional systems that you will have to maintain. You have to collect data, you have to verify it, you have to manage the resources and so on and so forth. So it's not that easy. Like machine learning, deep learning isn't as simple as we may have initially thought. And this is a chart that I used for a blog post quite some time ago with the wizard guy that is swinging his fiddle rod and making the car magically drive by some Python and some AI. And I think by now, pretty much everyone in the industry knows that this is not really working, and that it's like there's all of these self-driving companies that call themselves like something.ai in the end, as if it was the only important thing for realizing a self-driving car. And that's one application. It's actually the same with many other applications. This whole hype of deep learning is gone. We know by now that there is no magic of that machine learning, deep learning brings with it that just magically makes all of the problems disappear, and the engineering effort and the time that we have to spend into these systems to tune them and really get them ready for production. And what we have to do now is that we treat machine learning as an engineering discipline, which it really is. And again, forget about the hype. If we don't do that, then we will not be able to build safety critical applications. For that, it will not be sufficient to run a Python script and show that it's possible to classify images under certain conditions, and that's it. There's a lot of infrastructure that needs to be built around it, and there's a lot of things that we'll have to consider if we again consider it as an actual engineering discipline and not just as some kind of magic.
Felix, sorry for interrupting you. Your audio is a bit lacking sometimes.
Okay.
Maybe you can bit closer to the mic.
Okay, sure. If I'm too silent, is it better now for you?
Yeah, let's try.
Okay. Or give me a second and I'll see if I can increase the volume. A moment, please. Okay, I just put the microphone on max volume. I hope that helps, and I come closer to the screen. Is it better now, Florian?
If you stay in that kind of position, it seems to be better, yes.
Will do. Okay.
Thanks.
And the final statement on the slide was that Python is still great. It's not that this is really the problem. It's more a metaphor. So where should we begin? So we take the model, we fix it, we check the newest papers that we can find, we protect it against adversarial attacks, and we get more data because of generalization. That's a joke. So that's what very likely, that's something that people are doing already, and that people have been busy over the last couple of years quite much. But this is not the point. The point is really that we understand that we have a pretty long processing chain / value chain that we have to look at. We have specifications, we collect data, we label it, build data sets, we train and have a model. We use that model in applications, right? They are in the field, and maybe we have to retrain them, maybe we have to observe and monitor them. And at some point, we'll have to pull our applications, our machine learning-based applications, out of the field, out of service, right? And this is the primary focus of the presentation today. So within the scope of the white paper that we published with Tufsuit, we went deeply into that, and there is a machine learning lifecycle that we are proposing that I also want to discuss more in detail right now. And there is a reference labeling process, because that's a major pain point that hasn't been addressed very much so far. And finally, there's some thoughts on data quality assessment that I want to share in the very end of the presentation. I'll go on. So the machine learning lifecycle. This is the overall chart. It's pretty extensive. Let's zoom in. It's essentially different stages where we start with the specification stage, we go into implementation, into verification and validation, and finally we operate and commission the whole thing. And this basically applies for any machine learning based application that we are developing. And we start out with the motivation to come up with this with an application at all, right? We specify the use case, we specify how machine learning within that context is supposed to be applied. That can, for example, mean that we don't want to have recurrency, or we don't want to have any kind of memory in our machine learning system, because we consider that as a potential source of error. It could propagate errors, and maybe that's something we want to avoid. Maybe we also want to specify how big the footprint of the network is supposed to be. Nevertheless, that is something that probably pretty early in the whole development we can already pin down or at least constrain. And if we do that, then we'll have a data and labeling specification. Like if we define the task and how we want to solve it via machine learning, then already part of that should be that we should define which kind of data do we want to collect, where do we want to collect it, in a way that it represents that use case. And for the labeling, obviously too, so if we already know that we want to use machine learning, say for a semantic segmentation task within that whole application, then obviously at that point we are already able to provide a labeling specification as well, and we should do so at this early stage. And we also specify the model space. So again, how would the model be constrained in terms of memory, runtime, compute resources that we give it, and so on and so forth. So again, if we conduct the specification, we receive a couple of artifacts that we use later on. And we'd have to acquire the data. we'd have to select what we actually want to send to labeling, assuming a supervised machine learning setup, which is, I would say, very, very widespread among the commercial applications. And we'd send that to labeling. After labeling, we receive a data set, and we select all of that data set what we really want to use for training. And there's red QA bubbles for all of that, because every process step you can run quality assurance for, and very likely you also want to. You want to check that what you're doing there is making sense and is sane and safe. There's a couple of observations that I have that I want to share on this, which is first and foremost that this specification doesn't really happen. People usually jump right into the development, collect some data and have it labeled, but they do not necessarily sit down in the beginning and specify in detail what they need. And consequently, like a data labeling specification, well, you need some labeling specification in order to get data labeled at all, but it doesn't have to be very detailed. So it doesn't necessarily need quality targets or something. So more details, more sophistication. You can do an absolute minimum, and what kind of data is supposed to be collected. I've seen very often that this is not specified at all. And the model space specification, that's also often just trial and error. Maybe you have a rough runtime target and then you just go. So unfortunately, often this doesn't really exist. And again, consequently, the data you are collecting, if you don't think about it, may not be representative for the use case. And you may have problems with redundancy and bias if you don't pay very close attention to the selection of data you're actually sending into labeling. And then there's a problem with the quality of assurance of labeling, which is sometimes done with the labeling supplier themselves, who have a kind of conflict of interest, and sometimes done with the final customer or the developer of the machine learning application, which often doesn't have resources / interest to go really into detail here. And another interesting question is whether you, in your individual function, have ever checked the data sets you have lying around or you've been confronted with, if you have ever checked them extensively for consistency, for content, or is this just a dump of data where anything that was previously labeled goes into and it lies there, but there's no real intel about its details. So these are problems. Let's go to the next stage. This is the implementation stage. And within that stage, you essentially define how you want to explore the model space. So assuming that the model space is defined and you know what your models are, like what the characteristics should be, how much, again, memory, how much runtime, how much compute resources, which layers are allowed, which ones are forbidden, and so on and so forth. So assuming that you know what the scope is, you'd set a policy that defines how you explore that. So do you just train a bunch of networks in parallel and do you do some kind of grid search, or do you do this in an evolutionary way? So essentially, how do you come up with different models that you are training and testing? And this, you can imagine this like a generator of architectures, which will provide one architecture after another, and essentially gives you a model architecture. For that model architecture, you'd set the hyperparameters. This is a little bit machine learning speak, and I think I'll just leave it like this. Essentially, the training parameters of the training you use for that neural network or other machine learning model. And you have these hyperparameters, and together with the model, you can start training. You will obviously also need the data. So before we said there is data, you select something for training. You can still see the bubble over here. And so essentially you'll have training data, you'll have machine learning validation data, and you'll have machine learning test data. We put the machine learning in front of this because it's easily confused with actual verification, validation of the whole application, which is something different. And then you train. And then you, like as part of this inner loop of training, you will have checkpoints for which you run validation and for which you measure the loss and maybe additional metrics in order to decide whether that's a good model or a bad model. And this is kind of the inner loop where you have a model and you adapt the hyperparameters a little bit and then retrain it and try to get the best possible outcome of the machine learning validation. And there is also a kind of outer loop that goes all the way back to the generator that produces whole new different architectures for you. Again, it's not important whether this is done manually by an expert engineer or you have completely automated this, but it will end up being the same thing. The only post that I put on here is why would you run QA for that? So training, what's QA for training? It's simple. It's every single process step here can go wrong, and if you don't treat it with sufficient attention, will go wrong. The training framework, if it's some I don't know, homegrown framework that has never been assessed, never been verified at all, then it may produce wrong values for the loss. It may produce or the training of the networks may not be successful. May by far be under the potential performance, and so on and so forth. And for the training itself, there's also many things that can go wrong if that isn't being implemented properly. Same for the validation. I think I should go into detail with that, but maybe then another session. Otherwise, we get too deep. And then finally, there's the verification and validation phase, and there's operation and decommissioning phase. So you will verify that your application now, so you take the inference model that you built, right? And you will verify that within the scope of your application, it fulfills the requirements. That's the actual verification. And then you deploy it, which can also go wrong, right? Depending on how much, like now you're in a real physical system and you have a couple of additional effects that can come into play and that can decrease the performance of your application. So you do want to validate in the very end. You want to run that in the field and validate that all of your initial assumptions have been correct and that the way you have specified this is correct. That, for example, if during the early stages you never thought of driving at night, and then you go into the field, you drive at night, and realize that it's not working at all, that's exactly what validation should catch before you go into actual operation, which is the final stages. Again, maybe you have a fleet of robo taxis, maybe you have an individual I don't know, security camera that is machine learning powered. Anyway, you have it in operation and you probably want to monitor it to, for example, it is possible that the environment changes, that new objects occur, like there is these electric scooters that almost came into existence overnight, right? And machine learning systems that would be confronted with them would fail. They wouldn't recognize them if they have never been trained with data that with corresponding data, right? That's one of the reasons why you do want to monitor your machine learning-based applications / agents in operation. And there's decommission. So again, at some point, it may not be like some trained model may not be up to date enough anymore, and you may just want to get the model and maybe the whole robot or application, whatever it is, out of operation. There's a couple of more sticky notes here, but in the interest of time, I think I probably explained most of that anyway. In the interest of time, I'll move on now. This was the machine learning lifecycle. There's also a labeling process that we have proposed that may be of interest as well, because again, we found that the labeling is messy. It's very often you build huge data sets that, like nowadays, tens of thousands of data points, which may be images, is not a big data set at all anymore. That's like a small thing that you maybe do at the university. In the industry, you easily produce data sets that are hundreds of thousands, millions, tens of millions of data points big. And this sheer volume makes it difficult to still maintain an understanding of the quality of the data in these data sets. So there's so many labelings coming, there's so many labels coming in that nobody can really check them anymore, and then maybe somebody will check like do spot checks, and that's pretty much about it. And we found that this is just not reliable enough. It produces a lot of bad labels, and you cannot really fix with your neural network architecture what you've done wrong with the labeling. And that is essentially the motivation for defining that a little bit more. And essentially, it's three parties here. It's a data owner, so you as the entity that develops the machine learning application, and you control the whole thing. And the very first thing you do is that you have some raw data and send it to labeling. And the labeling party, they adapt their specification according to the source data. And they'll also have to adapt the tooling, everything, because they may not have seen this exact task or these exact kind of data before. Then there is a stage of automated pre-labeling, not always, but very often, that the data flows through. Then labeling is being labeling tasks, so this manual labeling is being distributed. The actual labeling happens, and the labels are merged, and then it's being sent back. And obviously, you have some feedback to improve performance. But nevertheless, labels come back from the labeling party, and along with the labels, there's usually a ton of concerns regarding the specifications. So if the specifications are bad or are not working for the data, the labeling provider would already raise at this point that this isn't working out, and that the specifications have to be adapted, which is a problem. So this happens really pretty often. And it would mean that at this stage, like we have one run through the thing and already realized, okay, actually the specifications weren't sufficient because there's differentiation between some classes isn't clean enough, for example. And then we had to go all of the whole loop and update the specifications and re-enter it again. You can imagine from the previous machine lifecycle that this is a pretty big step back. Anyway, let's assume that it does work out, and then we send the labeling to a QA entity. And this entity may be with the labeling provider, maybe with the end customer, it may be independent, it doesn't really matter. But we should consider it as a separate entity. And essentially, this QA party will do a pretty similar thing. They'll adapt to the labeling specification and the new source data because that may be new for them. They'll also have an automated, they have some automation that they adapt. They'll also have to distribute the checks and merge them at the end. It's pretty much the same thing, but it shouldn't be done by the same people in the same fashion with the same motivation. And consequently, they produce QA artifacts in terms of found issues and metrics on the data quality, and they trace just like the labeling provider, they trace as well whether there's a problem or not, and there's also a chance of realizing that this isn't working and we have to get out of the whole loop. Or it will be passed on, and in the very end, the owner, the developer of the machine learning application has to make the call whether he accepts the data, even if it is flawed, at least to some degree, or he rejects it. Good. So this was going pretty deep into machine learning development and labeling. The dataset quality, I think, is a little bit different perspective now. I hope it will also well, be a little bit not so much process driven. But anyway, so data quality assessment, I also wanted to shed some light on that. You all of these processes, that's good. But if you are in the situation that you build up a labeled data set, or you're dealing with one, you have to train based on one, then very first thing to consider is that you should put a QA process in place. You should regularly and systematically check the quality of your data. ideally yourself, but the most important thing here is that you put that into place. The worst situation is if this is just in the dark, if nobody really knows about the quality, nobody ever checks it. You you collect more and more data, have it labeled, put it on the pile, nobody ever checks. That's just the worst situation. You want to tighten checks if the quality is low, and you want to relax them if the quality is high. Makes a lot of sense. So if again, if what you get is underwhelming, then you should have an even closer look and really double check the incoming data. Second, you probably want to sample. So if you want to check the quality of your data, then again, if there's hundreds of thousands or even millions of data points, then it's going to be hard to check every single one of them. You probably want to sample, and you probably want to estimate how good the overall quality of the data set is, depending on the sample. And there's some formulas on the right side. I don't know, you could screenshot it, but also there's some LinkedIn articles that elaborate on that. But anyway, it's fairly straightforward to calculate how big the sample size is that you have to look at in order to reliably estimate how good the quality of the overall data set is. But if you have found all of these issues, you may want them to be fixed. And this is like the third aspect of it. If you want to fix them, it will also be a question, how much do you have to fix in order to reach a target quality level? And again, it's fairly straightforward to calculate that, but it's going to be way more than the sample size that you looked at least in most cases. So there is something to bear in mind, that it just takes you a very small amount of data to understand which ballpark of quality level you are in. But once you start fixing that and going out and improving the quality of all of these single labels, then that's not a very small set anymore. That's going to be a considerably larger amount of data. And yeah, so in the end, you may end up with checking the quality of a pretty large part of the data sets again. If you really want to fix all of that, you want to check them, you want to find the issues, you want to have them fixed. And in order to overcome that, yeah, you will need proper tools, and you will need some degree of automation in order to realize that. Okay, so summary. Machine learning is maturing, so we are getting all of that research stage. That's a good thing. There's a white paper that explains that has the charts that I've just shown you and explains all of that in detail. Maybe it's interesting for you, then please go have a look. It's public open source. For the last part, the quality of labels, there's a couple of LinkedIn articles that you can easily find online. I'll also post them later. And finally, I just want to raise that this transition to reliable machine learning development is hard, and I know myself how much fun it is to quickly experiment and show that something is working with a prototype. And it's incredibly tedious in comparison to get it straight and to get it to a level of quality that really enables a product. And that relies on the whole community and everyone that's involved to help move forward on that transition, to contribute and ideally contribute open source. Okay, that's it. Thank you very much. I'm open for questions now.
Thanks, Felix, for that great deep dive on AI quality assurance. For sure, we have a bunch of questions. So the first one is related to AI as an engineering discipline. So do you consider introducing a functional safety, design, verification, validation step, and hybrid approaches with AI and traditional engineering model, for example, for ASIL certification?
Yes, I think it should be covered in there, and I think that this is also on the way already. And that is something where the machine learning community probably should contribute and make sure that this is going to the right direction. like many of the patterns described in ISO 26262 are not great, do not fit well to machine learning / deep learning. But I definitely think that yes, it should be standardized. And again, machine learning, deep learning should be considered as a subdiscipline that maybe has some specifics that we have to take care of. It's essentially like implicit coding where we have the data determining the performance of the system and the reliability of the system. But yeah, it should definitely be part of standardization. And not something completely on the side, but you would want to have it as an integral part of a software solution.
Okay. The second question is, may I ask, what do you think about synthetic data sets for virtual ADAS and AD training and validation?
Very nice question that I didn't see before, but yeah. So I just discussed this recently with a friend, and the conclusion was for LiDAR. Well, let's put it in the scope of self-driving first, because it changes a little bit depending on the application. For LiDAR, we came to the conclusion that we don't really know what the problem is, meaning that you can. We're convinced that you can create synthetic data that is so close to the real world, and yeah, in many cases so close to the real world that you definitely benefit from learning from it. But for camera, it's kind of the other way around. We don't know what the solution. We said that we don't know what the solution is because the gap between camera data, like synthetic camera data, means essentially rendered 3D environments, and real camera data. The gap is so huge that like all experiments or pretty much all of the papers that I've seen point to the direction that this isn't working well. At the moment, you have like a fairly decent amount of real world data. You just get a much better performance out of your model if you train it with the real world data as compared to training it with the synthetic data. And the reason for that is that yeah, in the end, the camera data is more high dimensional than LiDAR data. There's much more information transmitted, and there's much more complex patterns that are being conveyed via the image. That makes it harder to synthesize. Yeah, so there's effects. On the one hand, there's a couple of effects in terms of dirt and stuff being bent and rain on it and so on and so forth. That is hard to properly synthesize. And second, there's just this incredible variety of models that you find in the real world that you cannot really synthesize well. So let me put it like this: in a simulation environment, you will have 20, 40 cars, maybe 200 if you're really going all in and making car models. And in the real world, you will have tens of thousands of different cars, old ones, new ones, ones that are partly damaged, ones that have been tuned and changed, ones with stickers on them that make them look entirely different, right? And this degree of diversity that you find in the real world, you can hardly achieve in any synthetic world by modeling that stuff individually, right? As long as we don't have a technology that can completely automatically generate realistic 3D environments, we have a massive problem there. And that's the missing solution. And sorry for this whole statement being very much focused on self-driving. It looks a little bit different for other applications.
Okay, so maybe a last question. Let's see. I'm not sure where this question is related to. Yeah, so I see one, and I think that let's take this as our last question. I think Felix, you are around. here in the meetup, so you can answer the question you're over LinkedIn. So last question, how often did you execute your workflow so far, and how often do you estimate to run through till your machine learning product is mature?
How often did I personally execute that workflow? Probably never. Never as sticking accurately to what we have proposed, and I think there's hardly anyone who did. And that sounds scary at first, but it isn't so much in the end. So the point is that there'll always be deviations. There'll always be specific good reasons to deviate from a reference process like we've laid it out for labeling, and the same for the machine learning lifecycle. But the question is how much you deviate. So whether it's that like in one point you don't again you don't have any kind of some requirements are missing that I've described, or some like you don't have an exploration policy, you just have an engineer who's trying out stuff. So it's easy to deviate in one point. It's hard to be in line with that reference process like 100%, but that's not really the point. If you have a good reason why you would deviate, or if you at least thought of an optimal solution and because of reasons you deviate from that, that's okay. But again, it's better to be able to provide reasons for deviating something from something. But anyway, that can be okay. But I would say that like I've been fairly close to this process many times, and yes, there were deviations here and there. And that for every other party that I've seen, again, there is probably not one process that will apply in really every single case, but if it applies often enough, and if most of it, like a big enough part is useful, then that's already an achievement.
Yeah, I think the kind of process must be tailored and adapted to the customer process, right? So, I mean, I think it's always good that to create a process that could be tailored and adapted towards the need from the customer, right? And if there are reasons to deviate from that, I mean, that's okay if you have good reasons then. Yeah. Okay, great. Thanks, Felix. There are a lot of questions, so please pass them to Felix directly, or you can reach Felix over LinkedIn. So we have to move on now, and I pass the ball back to Jake.
Yes, thank you, Felix, again for the interesting talk. And now you are filled with questions, so you have something to do. And now let's welcome our last speaker of this event, and also the last speaker of this year, Johannes Tangler from B+, and his topic is smart recording of high bandwidth data. Johannes, the stage is yours.
Thanks a lot. So thanks for having the chance to speak here. My name is Joe. Joe is fully enough. It's not Johannes Tangler, that's my father. Thanks especially to Florian, who invited me to this session. And yeah, it's late, but I'm pretty sure I will not steal your time, and I guess I've got some interesting content. So let me share my presentation. So there it is. And please give me a feedback, which slides do you see, the presenter mode or the presentation itself?
We are seeing the presenter mode.
So yeah. I guess now you see the presentation,
now it's
right?
Work.
Yes,
exactly.
Awesome.
Okay.
Great.
Did it. So the most challenging part is done. Okay. So B+ pioneering new mobility, that's our mission, and my speech today is about smart recording. Smart recording, as the title says, is for sure a little bit more than just a recording. So my presentation will actually introduce and teach you what to do if you want to develop a very good recording system. We will go through all the components. Components we already know. Everybody knows what's a recorder, what's raw data, and so on. Time synchronization and such things. And the interesting, or the more interesting, of course, part of the presentation is then what makes the recorder smart. So in the past few years, our customers always asked for recorders which are able to harvest. It's not just recording, it's really data harvesting as many bits as possible. So every bit is gold and so on. This was the slogan in the past years. Now they've got their storage full with petabytes of data. And actually, most of the time, or very often at least, they ask themselves, yeah, what did I actually record there? Can I need it? What was the firmware of the device under test while recording? What was the measurement setup? What was the time base and so on? So very much amounts of the petabytes of data are not really useful afterwards. And yeah, Felix, for example, had a very good point. The question, which piece of all the data I have shall I give to a very expensive step, the labeling step? This is exactly one question my presentation will answer. What can we do to just keep an eye on the corner cases, which we're really interested in, that makes the recorder smart in the end. Okay, so don't worry, I will not start the boring company presentation. Take out the information from this slide you're interested in, and I will go ahead to what exactly B+ does. So you can see 3 main areas of action of our business. The in-vehicle recording, that's exactly the portion of our business I will talk today. Recording in any kind of vehicle and smart. Analysis of the sensor data or any kind of data you collected. This is our business which we support with our tool chain. Hardware in the loop in this picture doesn't really mean in the loop. It means reprocessing or replaying. That's where we have solutions. Software and algo development is done in a team we all have in B+. And ECU software, that's actually not really our part. Of course, we can support you. We've got expertise in AUTOSAR, classic adaptive algorithms, and so on. Okay, let's step in vehicle recording. Recorder components yesterday and today, that's exactly the components you might know. So which components in hardware and software were and are needed? First of all, we've got an eye in ADAS AD on raw data. Raw data, every pixel counts in this context. We need it for training of our machine learning algorithms. We need it for verification, validation, and so on. So raw data means don't compress it, or at least don't lose any information. If you really want to compress it while you're recording, if you can afford the CPU or GPU power, then of course you might compress it, but never miss a bit. Okay. High bandwidth data, that's exactly what our customers ask us many years. So they first ask us for just 1 GB per second. Since a couple of years, they ask for at least 8 GB per second. Yes, we did that with the components you see. We are ready for more than 11 GB per second. What's necessary for 11 GB per second? Well, you can't work with a CPU, for example, which pulls or pushes data. You really need server technology here. We found the server technology and use it in our components from Mellanox, actually, Bluefield. And this allows us to use twice 100 gigabit per second data rates, and most important fact, without need of CPU. Okay, so we've got on a recorder instance all the CPU power we have for the recording, the data collection process, and we don't have to spend a lot of CPU power to just shift the data to a SSD storage or wherever. Okay. So, oh, just by the way, what might be very interesting as well for such high data rates, a switch. And of course, again, it's got to be extremely fast. Okay. So next step is, of course, data protection. Data protection in a perfect way would mean a end-to-end protection. End-to-end protection again would mean you've got to start where the data is really originating, so inside a sensor or a ECU. That's of course what we can support, but of course we've got to have the access. So the sensor vendor, for example, has to allow us to really step into his sensor, his ECU, because we of course have to get the data out. Then we can feed our recorder with that. Okay, end-to-end protection, for example, means that we or you have to take care about data integrity. That means using checksums or using counters, for example, in order to check if there is any frame missing, no matter where it comes from. The bus communication, CAN, LIN, FlexRay, Ethernet, or if it's really a ADAS sensor data. Okay, data protection, and very, very important, in my opinion, time synchronization. So time synchronization means, of course, we have to have at least one common time for the whole system. We have to share or distribute, deploy, call it however you want to call it. We have to distribute this time to any kind of measurement data interface, if we use any, and of course we have to use any to get the data streams, the different ones. So we have to distribute a time, and the time of course has got to be a good time. What is a good time? A good time means it's absolutely not allowed to jump. Not forward, not backward, both is not acceptable, okay? So this is why we use a so-called working clock, actually free running counter from our recorder system in hardware. And we've got an eye on deploying this time. That means we use IEEE 1588 standard, especially profile 802.1 AS. My opinion, a lot of other suppliers for recorders and measurement data interfaces rely on this standard as well. That's great, of course, and I think it's the right decision. Okay, for PDP time synchronization, you of course have to make sure you get RX and TX timestamps really on a hardware base. It's not allowed to have a software layer, for example, even not with high priority to get some timestamps, because a propagation delay, for example, between a recording system, which provides the time, the system time, and a measurement data interface has to be compensated, and that makes high precision data timestamps necessary. Okay, so what do we have in total? Components you actually might know. So on the lowest level here, the sensors, followed by what I called measurement data interface. Measurement data interface is of course needed to first of all make timestamps in hardware and decouple a data stream. So typically from cameras you get a LVDS data stream, no matter if it's GMSL or FPD link. And what we are interested in is normalized data streams based on Ethernet standard, base T Ethernet, and that's exactly what we provide to our recorders. A switch in this illustration is of course not a mandatory part, but when it comes to really high bandwidth and you've got to share or distribute your data, your raw data, then of course it's a very good idea to have a switch. As you can see in this picture, maybe it's of course essential to have a switch which is not only fast, but also a so-called time-aware switch. So a switch has to be used in this setup for time distribution as well, not only for data distribution. Well, a recorder system, of course, if you want to have a good one, make it scalable. And of course, as mentioned, it's a good idea to have it up to 10 gigabyte per second. And storage, of course, is not necessarily a separated storage, but of course can be a SSD system, typically a RAID system, if you want to reach the data rates. And yeah, maybe a good idea is to get it plug and play usable. So take the storage out, give it into a copy station, and then you can immediately go ahead with your test drive. So all of these, well, pretty well known components. And now let's think about to get this system even smarter. So first component first piece is what's a smart recorder? It's got two main components: make it intelligent and make it efficient. What does that mean? Okay, first, just something which is pretty new. I already mentioned IEEE 1588 standard, 802.1 AS profile, PTP. But what is pretty new since beginning of this year? This is the multi-time domain feature of 802.1 AS especially. So why do we need it for our smart recorder? Sharing one common time base for the whole system is of course absolutely necessary, it's mandatory. But you as an engineer who at the end has to work with this data, you are maybe interested in, for example, a GPS or based timestamp because you've got a system which is distributed over more than one vehicle. You've got any vehicle to X system, for example. So you need a time base, which is again common, of course, but is now based on a GPS signal, for example. So every component you have in the whole system, so your system in this example doesn't end with the recorder. It's got the external components, the other vehicle, the other traffic lights, for example, and so on as well. So this means you have to decide for another time base. Nevertheless, you don't want to use the high precision time base you have in your recording system. And this is a good reason why you have to, or why you should at least consider to use two time domains. Another example is you as an engineer in the end have a need to really see the time your device under test, your ECU, your ADAS ECU, for example, was able to see while running. And that means your device is, for example, connected to a AUTOSOR global time on CAN, on FlexRay, on Ethernet communication network. So you really have to have the insights of exactly this network, especially the time on this network. It's not only the data, but also the time on this network. So good reason why multi-time domains, and of course you can recalculate each time domain to each other depending on which focus you have. Okay, so very essential in my opinion. Your smart recorder should deal with multiple time domains. Okay, that's just an example how we do it. You've got to configure it, you've got to observe it, and of course you have to check if really propagation delay is compensated. Okay, next, and a very essential component to get a smart recorder is to make it intelligent. Typical recorders, of course, are able to collect data, high data rates, for example, from multiple sensors and so on, but now get it intelligent. Intelligent means we want to detect relevant scenes or relevant objects, whatever we search. Then, of course, we get from a algorithm, of course, we need in our vehicle. We get some meta information, of course, about the objects, the scenes we detected. What can we do with this meta information? Yes, we can get an intelligent recorder by triggering this recorder. Of course, our recorder has to be able to work with a pre and a post trigger. So, of course, we get the trigger, but of course, we want to know what's, for example, 10 seconds before this trigger. This is most probably the most important data we are hiding for. And of course, after the trigger, of course, we might be interested in the data which comes in even more. Okay. When we have metadata, we are able to filter the relevant scenes by triggering the recorder. And yeah, actually, we put a lot of CPU or even GPU power to get this meta information. So it might be a good idea to feed this meta data back in our recorder, because of course we want to use it afterwards. For example, filtering the raw data we connected in our backend. Okay, so what do we need? We have to add in our recording or in our system setup a high performance system, which is able to run not even just a single one, but of course as many as we need. If we've got the chance and the power, of course, in the car, we need a lot of CPU and most of all a lot of GPU power for our algorithms, which might, but of course might not necessarily be AI algorithms. Okay, so we've got a intelligent recorder. Now let's do the next step to get it smart. We need efficient recording. And what can we do to get a recorder which is far away from our office? What can we do to get it efficient? We have to get it connected. Connected means we've got to have a remote connection from our office into the car, or at least in all the cars we are interested in to observe. And what can we do with this technical setup? We can, for example, roll out driving task for the operator, for the driver. That means we have to deploy the measurement configuration. We have to deploy the algorithms which shall be executed on the high performance system to get it intelligent. We have to, for example, deploy firmware updates for our ECUs, for our devices under test. We've got to probably update the driver dashboard, so the information our driver is able to see. Maybe it's a good idea to tell the driver what's the mission. What is he hiding for? Shall he go to the highway? Shall he search for many trees on the road? Whatever. And of course, we should give the driver a chance to see if he did all we expect. So if he's on the right track, for example, or whatever. What can we do in addition? When we have a remote connection to our intelligent recorder, we can monitor, for example, the system health state, temperature, CPU, GPU utilizations, and so on. And of course, and that really makes it smarter, that is, we can really check how many of our corner cases we already collected, and not only from a single car, but all the cars from our fleet. That's very essential. So as a fleet manager, and of course we in addition need a fleet manager tool to roll it out, to check for the status and to check for our mission results. In this fleet manager tool, we of course have to observe all of our cars from all of our fleets. So we immediately have to know if we collected enough of our corner cases we are hiding for, and that is the point of time where the fleet manager can stop one mission, one campaign, and roll out another campaign. And all the drivers are immediately aware of what's the next mission they shall hide for. And of course, they need the information that their system in the car's trunk is prepared already. All the components are installed or updated for the new mission. Okay, so we've got our smart recorder. We've got all we need to get it intelligent. Lots of CPU and GPU power, which is able to trigger a recorder. We've got a connection, a remote connection. So we really have a efficient system now. We really can control as a single person, as a fleet manager. So that's what, in my opinion, makes a recorder really a smart recorder. So that's how it looks like then in the end. Our sensors, of course, our measurement data interfaces, optionally a switch. And of course, now you can see it's maybe not a bad idea to have such a high performance switch, because it allows you to distribute and even select the data streams you want to have at your high performance PC or directly send to your recorder or whatever. The computing power here, the recorder itself, optionally a external storage, or might be an internal storage as well, and not necessarily, sorry, by a piece of hardware. It's of course possible to do that with a recorder as well. It's actually software at all. The connectivity solution. Okay, something's missing. Yeah, a piece of software could be helpful. Very essential. We've got a framework. A framework, of course, is not just a recorder application. It allows to integrate to other solutions. It allows to integrate other frameworks, other C code, user-specific C code, and of course a recorder graphical user interface like a visualization interface is just one of the possible application you can do based on a framework. What you can see here is an example we do with a partner in a cooperation. I'm really allowed to say that it's Siemens Mentor, but of course we've got many cooperations. One, of course, you might know is with Insenda. Sure, I'm allowed to mention all the other colleagues from the Data Garage setup. So IBM, Lenovo, Bertrand, which did a very good, who did a very good job with our new demo car. Yeah, that's very essential to have a solid software base. And yeah, this is just an example how it might look like. You see Avito app connectivity, so the fleet managers tool, a driver dashboard where of course the driver is allowed to tag. So I just mentioned main components for recording. There are of course multiple more. But let's just concentrate on especially the components which make our recorder smart. You've got to visualize that, of course, not necessarily maybe during test drive for the driver, but of course, when you get the system into operation at the initial state, the developer, the development engineer, sorry, of course, needs a chance to check if the camera data is coming in correctly, and not only the information, is there data coming in or not. Okay, the picture on the right-hand side at the bottom shows you current setup in our demo car. And yeah, you can see it's a lot of hardware, of course, needed, but this, of course, illustrates or sets up a very huge setup. So we've got all the components and not only a single time. Some of them are really twice contained, so it's not necessarily that huge. Doesn't need always your full trunk. Okay. So that's actually what I wanted to tell you. In the picture here, you can see all the components again, which are necessary for a recording, especially for a intelligent recording system. And yeah, by ingesting this data, you already have you only have to ingest what you really searched. And in the data center, then of course you can make the next steps in running another algorithm or multiple algorithm to even further select what you're really interested in, and that's exactly what you might give to a labeling instance. Okay, thanks a lot for listening. Hope there are many questions.
Yeah, thanks. Thanks, Joe, for that really illustrative talk. I already see a few questions here. So let's start with the first one. Here it is. The first question is, can you also collect data from ECUs on the CAN bus, e.g. from engine, transmission, steering, or drive-by-wire components, for instance?
Yes, so actually CAN, for example, of course, this is a common bus communication system. We also have hardware for base T1 Ethernet, for example, and as mentioned, and that's really essential, we've got a software framework. So our mission actually is not to integrate any kind of sensor you can find, any kind of source you might be interested. We try to have at least the main ones, so camera interfaces, of course, bus communication interfaces. We've got access to NMEA data by a GPS antenna with our system. Our intention is to provide the framework and to provide, of course, all the necessary hardware components, but of course our customers shall be enabled to make their own data sources, whatever they are interested in, and of course they are able to, as one picture, this for example illustrates, to bring in their own source code and to even design their own visualization elements. So we can't have any kind of sensor connected, we can't have any kind of algorithm, we can't have any kind of visualization element our customers might be interested in. So it's really the tooling we provide, and of course we can help you until you have the solution.
Okay. So next question is, how do you ensure the separation of time sync messages in the system, DUT, I think it's device under test, versus your measurement setup? I think it's a kind of question how you provide freedom of interference between that components, between the system under test and the measurement setup.
Okay, so this pictures show at the left-hand side our configuration tool, and on the right-hand side our XTSS monitor for time synchronization purposes. So, well, it always depends on the total system setup, which times have or time domains really have to be taken under consideration. When we just have to focus on a local system, then it's a good idea to have the recorder itself as the time master. It can deploy its time to measurement data interfaces. And of course, when data streams, in our example with our hardware, come in directly as Ethernet data streams, of course, we in hardware make our own RX timestamps. It's a little bit more tricky when you really want to get, for example, out of our global time, because you've got to derive it from exactly the source which you want to measure. So that's not as easy as just deploying from a recorder to other instances of the measurement system a time. How can you do that? You, of course, measure the raw data streams, the CAN frames, for example. And of course, you do what you always do with your recorder. You just measure it, make your data protection jobs, give it to a SSD storage, for example. The pure recorder job is done. And what you can, as a next step, and of course in parallel do, you really can derive the out-of-the global time information, for example, from the received raw data stream. And having a measurement data interface, and these interfaces are of course available, you really can use this measurement data interface to derive the global time on CAN data information. And then of course you've got to configure your measurement setup, your recorder system, to derive the time from the measurement data interface. So the measurement data interface is this time origin, and you provide this time to your recorder, and then again the recorder shares this time with all the other measurement data interfaces. Okay. Please keep in mind that you, of course, most of the time are not interested in just a single time. It's more than one time domain which is typically interested. So again, back to our example, it's probably not only out of our global time on CAN you're interested in. You might need a tie time, for example, as an alternative time as well. Okay, hope understood the question right.
Yeah. The other question is, what do you make of the hype, let's say, when 5G is available everywhere?
Yeah. When you can transfer 10 gigabytes per second wherever you are, and let's say at least in Germany, then 5G is a very good option. then you can save a lot of money in storages. Yeah. As far as 5G is not able to do that, it can help for the connectivity purposes. That's my opinion, at least. Okay, so in my opinion, it's not the main focus to have a very fast, like 5G, connection to your vehicle, to your fleet. It's even better to have a reliable, a robust connection. But actually, that's my opinion. Others might have another opinion. But of course, having 5G is at least better than having just 1G.
Okay, then I think we will come to the last question. So how much compute power you expect to need for the intelligent recording? You mentioned AI algorithms. How do you map that to CPU or GPU units?
Okay. How to answer this question? As much as possible is a good approach, in my opinion. And as much as possible, no matter if it's CPU or GPU power at first glance, is typically limited in a vehicle based on the generator you have. So the vehicle can provide a limited number of unlimited power, sorry. So what is possible, and that's like our system is designed, we expect about 2,500 watts in electrical power, which we can feed into CPUs and GPUs. And from our understanding, that's pretty much what you can have in a car. So this is a limitation which is fact. So even if our users would wish for more or would ask for more power in CPU and GPU, they have to provide the power which is needed to run such systems. Well, then of course, one mission is to provide the data. How to provide the data? I hope I was able to depict that. You might use a switch, you might use data forwarding solutions. A data forwarding, in my opinion, again, has to be a solution which not necessarily needs a CPU, because the CPU shall work as a recorder, shall help the recorder to do its job and not just push bits and bytes. Yeah, and then what we can provide as a tool is, of course, the system, of course, with liquid coolage and so on, to be equipped with many CPU and GPUs. Well, and then, of course, it's up to your environment, which you prefer, where which algorithm is executed.
Mm-hmm. And I think based on the kind of algorithms that will be integrated, you can, I think, scale it from the compute performance needs.
Yes, of course. So our system basically comes with 2 CPUs and 1 GPU, but of course we are able to run up to 5 GPUs, for example, and we've got 7 PCIe slots. If you might use a FPGA PCIe card, for example, yeah, that's up to the user demands.
Mm-hmm, mm-hmm. Now I see we got, now that's really the last question. So, but I think that's a really interesting question. So any ideas how to bridge the gap between what you are proposing in the smart recording and what presented as expected by the audience from a car during development? So how you can combine your recording with the first talk. So that is interesting.
Okay. Well, again, what we can do is provide the tools. The user, of course, has to decide how he wants to use it. And well, like both talks before, picked it out. It always depends on the algorithm, how the algorithm is trained when it's machine learning. approach, how good the algorithm is programmed when it's a classical algorithm. What's pretty hard from my understanding, to come to the first presenter, is how can we detect or identify what a human driver sees, what he perceives and so on. This is pretty hard because we just have our algorithms, and yeah, we can't connect to a human, a man's brain, for example. Yeah, that's pretty hard. So we just can do this step afterwards, so we can see what a algorithm recognizes, and we can of course show the same environmental variables, all the videos at least, to a human person, and this human person then really can, what we typically call ground truth, can tell us what would be the right decision a human driver would have taken.
Okay, so yeah, thanks again, Johannes, for your talk and for answering all that questions.
Thanks for inviting me.
Yeah, sure, you're welcome. And then I pass over to Ching for the last, or for the conclusion today.
For the conclusion, yeah. So thank you very much, Johannes. Also, thank you for Florian. So now we are reaching the end of this event, also the end of like the virtual event of this year. And thank you very much for participating. It's your participants which drives us, our organizers, to keep this virtual meeting format. And we'll continue doing this in the last year. And there are several announcements. And the first one is we'll put our slides of today's presentation, of course, also previous presentations on the website. You can check in the chat. So Florian will put the website in the chat. And the second announcement is that since we are recording this meeting, and we'll also put the recorded video to our YouTube channel. So in the future, if you pass the meeting, you can check the presentations in our YouTube channel. Yeah, you see that now we are moving towards like YouTube influencers, and I think that's everybody pretty much doing during the pandemic time. So I hope you enjoyed the virtual meetup, and looking forward to meet you again virtually, and also even like physically if it's allowed again. And thank you very much. Hope you have a nice evening, and earlier Merry Christmas to all of you.
Thanks, guys, for joining. Take care. Stay safe.
Take care. Stay safe.
Bye.